anybody, but if it does help one student, I'm happy. Okay, here's the mean value theorem. Here's a function. First, the hypotheses have to be the same, the first two hypotheses from the Rolle's theorem. The function has to be continuous on the closed interval a comma b. The function has to be differentiable on the interval a comma b. The third condition doesn't apply here. It's not necessary here. So they're the same first two from the mean value theorem. Let's say we have a point here, and let's say we have another point here. This is point A and this is point B. And this is function f of x, of course. I'm going to draw the line segment AB. I'm going to find the slope of AB. This is A, this is B, of course. The coordinates of A and the coordinates of B will be, of course, A, comma, thank you, and then f of B. So I'm hoping you will agree that the slope of AB will be, if anyone would like to help.
F of E minus F of A.
Thank you very much, Tom.
At the top of E minus F.
Perfect. Awesome. And here's what I'm going to do next. I'm going to draw parallel lines to AB sequentially till one of them becomes the tangent. So parallel lines to this till I get to draw a tangent to the graph at this point. Okay, so if the function is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a C in the interval a comma b such that now I'll wait for you to tell me what to write. What do you think?
F prime C is equal to.
Exactly. Thank you very much. This, the C is guaranteed by the mean value theorem. Okay. Let's see how this works. On page 289, let's start with problem 9. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers C that satisfy the conclusion of the mean value theorem. So we are given a polynomial function. It's quadratic, 2x squared minus 3x plus 1. And we are given the closed interval 0, 2. Verify that the function satisfies the hypothesis of the mean value theorem. And then find C, guaranteed by the mean value theorem, that says that f prime of C is f of B minus f of A or B minus A. Of course, this is our A and this is our B. So for number 1, would you agree that this is continuous on the interval 0, 2 as a polynomial function? It's a polynomial function, it's continuous everywhere. Would you agree that for the same reason f is differentiable on more than the open interval 0, 2. For the same reason, is differentiable everywhere. Would you agree? So then there is a C guaranteed by the mean value theorem, then by the mean value theorem, MVT, mean value theorem. There exists a C in the open interval 0, 2, such that, and now I have to find f prime of x. So such that f prime of C is 0. So now we have to find it. Have to find f prime of x first, which is 4x minus 3. In order to solve this equation, all I have to do is write 4c minus 3 equals 0, and I get the c equals 3/4. It better be between 0 and 2. Why? Because it's guaranteed by the mean value theorem. So that tells us that there is a point where the function doesn't have a term necessarily. It could. Doesn't have a term. But there is a point whose derivative is determined or can be determined by the slope of the tangent line, by the slope of the line passing through AB. Any questions?
So you've got by MDT f prime of c equals 0. Isn't it going to be that the f prime of c equals the slope of AB?
Yes, of course. I wrote, I was still thinking of Rolle's theorem. Sorry about that. Absolutely. Sorry about that. I'm thinking ahead. I shouldn't. Okay. So f prime of c equals f of 2 minus f of 0 divided by 2 minus 0. Thank you. This was not checking whether you were asleep or not. I was asleep. Such that f prime of c equals f of 2 minus f of 0 over 2 minus 0. This is not Rolle's theorem. This is mean value theorem. Thank you. So we already have f prime of x, which is 4x minus 3. We have f prime of c, which is 4c minus 3. Let's find f of 2, and let's find f of 0. F of 0 is 1, and f of 2 times 4 is 8. 8 minus 6 is 2. 2 plus 1 is 3. Thank you. So 4c minus 3 equals 3 minus 1 divided by 2. If you want, minus 0. So 4c minus 3 equals 2 over 2, which is 1. Therefore, 4c equals 4 or c equals 1. And as I said, it better be between 0 and 2. Guaranteed. Any questions? I think we should do one more because I probably confused you and I don't want to do that.
Just,
Yes, please, Tom.
the little symbol, I keep getting such that and then the other way.
So this is including. So is in. So this is in. This one is such that.
Gotcha.
This is such that. And I'm sorry, such that, and this one is there exists. So there exists a c in the interval 0, 2 such that, this is false, such that f prime of c equals f of 2 minus f of 0 over 2 minus 0.
Gotta remember which way.
Yeah, so there exists, this symbol says, means is in, there exists a c in the interval 0, 2, And now the condition, such that f prime of c equals f of 2 minus f of 0 over 2 minus 0. Okay, let's look at one more. Let's say 12. We have f of x, which is 1 over x, and the interval is 1 comma 3. So condition number 1, or hypothesis number 1, is f is continuous on the interval 1 comma 3. And you can say, wait a minute, it's 1 over x. Yes, but this function is not continuous only at one point when x is correct. So between 1 and 3, definitely the function is continuous and differentiable. F is differentiable on the open interval 1 comma 3. Then there exists by MVT, there exists a C in the open interval 1 comma 3 such that f prime of C equals f of 3 minus f of 1 over 3 minus 1. We find f prime of x, which is negative 1 over x squared. This is very handy to remember, right? 1 over x prime is negative 1 over x squared. The left-hand side is negative 1 over c squared. The right-hand side has 2 in the denominator, and I have to plug in 3 and 1. So it's 1/3 minus 1. Any questions so far? So we'll simplify. We find the least common denominator. Let's see what we get. Negative 1 over c squared equals, the numerator is 1 over 3 minus 3 over 3, right? So negative 2/3 divided by 2 over 1. I'm getting ready to flip the denominator. So negative 2/3 times 1 divided by 2. I will simplify by 2 and at the same time multiply both sides by negative 1. And obviously I get c squared equals 3. So here's how the equation looks before this. So 1 over c squared equals 1 over 3. If two fractions are equal and they have the same numerator, they have to have the same denominator, or just cross multiply. So therefore we take the square root from both sides, and we have to get two solutions, plus or minus the square root of 3. Only one of them is in the interval 1 comma 3. So I will say no, only c equals the square root of 3 in the interval 1 comma 3. And this is the x value guaranteed, where f prime of c equals f of b minus f of a over b minus a by the mean value theorem. Any questions? Any questions? Is this okay? Okay. As I said, we can look at some applications with both Rolle's theorem and mean value theorem, if you'd like. My department decided that presenting the two theorems and doing simple examples or applications is good enough, but if you decide that we should go and look at more examples, let me know. Okay? Continuing with 4.3, the title of 4.3 is How Derivatives Affect the Shape of a Graph. I would like to change that title. Of course, it's not important. But what the title really is telling us is what we learn about f of x studying f prime and f double prime. I think that this should be the title of this section. What we learn about f of x, studying f prime and f double prime. What do they say about the function? Okay, so first of all, f prime of x is connected to what is called the first derivative test. First derivative test. Of course, the second derivative will be connected to the second derivative test. I personally very rarely use it. I will show you what it is, and I'll let you choose if you prefer to use the first derivative test or the second derivative test. They're both legitimate. They're both wonderful. For me, it's just a matter of habit. I use the first derivative, and I'll show you the difference between the two. But you feel free to decide which one you prefer. They're both doing the correct job, so it doesn't matter, really. Okay, so what does the first derivative test say? It says this, that if we have a critical number, if we find that the function has a critical number, determining the first derivative and setting it equal to 0, or finding x values for which f prime is undefined. Now let's say we find critical numbers. Let's say we find one where the first derivative is 0, and the left-hand side is a positive sign of the first derivative. So the first derivative is positive 0 and then negative. So here's what happens. If the first derivative, left and right of a critical number, follows this sign, it's positive, then it's 0, and then it's negative. What type of point is this? The critical number really turns into what type of point? Very good. This will be a max. It could be local. It should be local. It could be global or not. We'll see. Okay, what if we have this situation in which the derivative is negative, then it's 0, and then it's positive? Yes? Now, what does this mean when the first derivative is positive? What does it say about the function? That the function is increasing. So when the first derivative is positive, the function is increasing. When the first derivative is negative, what does the function do? Decrease. So f of x is decreasing and f of x is increasing. Okay, let's continue. There is more to this. What if at a critical number the derivative is undefined, and of course the function is defined, and we have this sequence of signs? What will that x become, or that point become? Or nothing. Remember, the function has to be defined here. The derivative is not. It's still a max, no doubt. What if we have the same situation, but the signs are reversed? What will that point become? Perfect. What if I have this situation? Either 0 or undefined, but the left-hand side and the right-hand side have the same sign. So the derivative is 0 or undefined, and it does not change sign left and right. Not a point of, we say, extrema, and we mean max or min. By extrema, we mean either max or min. So what we learn from here is this. If the derivative is 0 or undefined, and it changes sign left and right of that point, the critical number changes into a max or min, depending on the sequence of signs. But if the derivative is 0 or undefined, but the derivative does not change sign left and right of that point, that will not turn into a point of extreme. So that's how some critical numbers become max-min and others do not. So it's not sufficient to say that the derivative is 0 or undefined. Not sufficient. I have to show that there is a sign change, either from positive to negative or from negative to positive. And then the function has a max-min. If it does not change sign, the function does not have a max-min. Okay? Now let's look at a function. We have to look at I think that's the easiest thing to do. Look at a function, study the first derivative, determine max-min, and then talk about the second derivative test. Because I think it's, if I just give the second derivative test, it's going to be kind of difficult to understand. Let's work on a problem, and then we'll look at the second derivative test. Okay, so let's pick from page 299. Let's try to find an easier situation. Not a radical yet or rational yet, just anything else. Like, let's take a look at 38. Or you can choose. If you like to choose, please do. So 38, age of x. 5x to the third minus 3x to the fifth. We're asked a lot of things here. Among which, find the intervals of increase or decrease. Find the local max and minimum values. Find the intervals of concavity. We haven't talked about that yet, in a minute. And the inflection points. Use the information from parts A through C to sketch the graph. A lot of work. Okay, so first of all, I would like to identify the type of function we picked. What type of function is this? Awesome. Secondly, I will rearrange it in the correct order. Next, I will factor out negative x to the third and get 3x squared minus 5. This is the preliminary preparation for the function. Okay. Next step, I will find the first derivative, which is 15x squared minus 15x to the fourth. I will factor out negative 15x squared this time, and I get x squared minus 1. I should have differentiated this not to confuse you. As negative 15x to the fourth plus 15x squared, and then factor out negative 15x squared. Continue factoring. Negative 15x squared, x plus 1, x minus 1. So far, nothing new, really. We just rearranged the function. We found its derivative, and we are getting ready to find the critical numbers. So let's figure that out. H prime of x equals 0. I hope you agree that there is no critical number coming from h prime being undefined, because this is a polynomial function, is always defined. So critical numbers can only come from h prime of x being 0. And I see 3 critical numbers. And they are
0 and negative 1, positive 1.
Thank you very much. Very good. So let's get our table. X. First derivative, h prime. The function in the middle. And the second derivative, last row. This is the table I recommend. If you would like to create your own, that's fine. Whatever works. If you like a different order, the reason why I put the second or the function in the middle is because when we get to graph this, you will see everything will come together in the middle. But it's up to you. Okay. I have to start with the domain of this function. Can anyone give us the domain?
Let's say parentheses -1 or just -1
So this is a polynomial function.
or negative infinity.
Correct. So we're not talking about, we're not studying the function on a closed interval. We are given the function. Maybe that wasn't clear. That's my fault. I'm sorry. So we're given this function and we're asked, find everything about it. And then at the end, graph it. Anything that you can think of. And there is a list of things that we have to determine. However, the moment we completely fill this chart up or this table up, or fill it out with all the information that I'm going to show you, you're done. And you're ready to graph. You'll understand in a minute what happens here. As you remember, always the first example takes like forever, and then the second example will be 5 minutes. But the first one I have a lot to say about. Okay. So in the table at the top, I will put 0, -1, and 1 in the correct order. -1, 0, and 1. The first derivative, as you already mentioned, is 0 at those points. My next step is to find the sign of the derivative in this interval, in this interval, in this interval, and this interval. I have several ways. One will be to simply plug in numbers. Second option would be is to realize that this is always positive and this will not affect anything. I don't even have to plug in anything in this. And I know that this is a quadratic function crossing at -1 and 1 with a negative leading coefficient. Crossing at -1 and 1 and with a negative leading coefficient. So it has to be positive between -1 and 1 and negative outside. You can say, I don't want to think in those terms. I want to plug in a number. Fine. Let's do that. So not in this. It's useless to put in, or a waste of time. So let's say I want to plug in -5. Negative, negative, with negative. So it must be negative. Now in here, I have to plug in -0.5. Positive, negative, negative. What is the sign? Very good. In here, I have to plug in 0.5. Positive. Negative. Negative. So one more time, with -0.5, this is positive, this is negative, this is negative. With 0.5, this is positive, this is negative, this is negative. Agreed? Okay. Now I plug in 10. Positive, positive, negative. Exactly what we said, right? Between -1 and 1 is positive. Outside is negative. Perfect. Next step. I need to find this, 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 and I'm going to ask you what am I referring to here, and what am I referring to here? So first I'm going to plug in -1 in the function. So this is +3, and this is -5. So -1, +3, and -5. So this is -2. With 0, clearly it's 0. With 1 is 5 minus 3, which is 2. But when I say I have to put something here and here, what am I referring to? Of course, thank you. Limit of the function, okay, it's h of x, as x approaches -infinity. And the other one, limit of h of x as x approaches infinity. Let's go back to the function. And please identify which of these two is the most powerful one that comes into play that we should discuss when we talk about infinities. Only when we talk about infinities. Which of these two? Of course, just this. This is the most powerful. This is too small to count. It will not overtake this. Okay, so when x approaches negative infinity, where does this go? Correct. When x approaches infinity, where does this go? We agree? Because this is infinity times negative 3. So negative infinity. Perfect. Okay, one more step. But that can wait. That can wait, just 1 second. Now, at this point in time, this is right here, right now is the moment of truth. This is when I catch my mistakes. If these two rows do not work well together, I'll say, oops, there is an error somewhere. Okay. What does this function do from infinity to negative 2? Right. Is that supported by the sign that we determined for the first derivative? Yes, we did. Perfect. What does the function do between negative 2 and 0? Is that supported by the sign we determined for the first derivative? What does the function do from 0 to 2? Okay, is that supported by the sign? And what does it do from 2 to negative infinity? So now I know that these two rows communicate well together. Okay. Next step that I have to address is this. What type of point is negative 1 comma negative 2? The derivative is 0, so it's a critical number. Negative 1 is a critical number. And the derivative changes sign left and right. It changes from negative to 0 and to positive, or from negative to undefined positive.
Relative min.
Perfect. So this is a relative min. The derivative is 0. So 0 is a critical number. What type of point is 0 comma 0? Nothing yet. Why? Because the derivative does not change sign. This point will not be a max or a min. Okay, next one. What type of point is 1 comma 2? Yes, because it starts with positive, 0, and negative. So this is indeed a relative max. Perfect. Very good. So for now, what will I say about this function? I will say it has a relative min. I would say it has a relative max. I would say it's decreasing on the interval negative infinity to negative 1 union 1 to infinity. And it's increasing on the interval negative 1, 1. Would you accept that? So because the derivative is negative, the function is decreasing on negative infinity to negative 1 union 1 to infinity. And it's increasing between negative 1 and 1. Agreed so far?
Would you have to exclude the point where it's not increasing to the equals
Yes,
0?
that's why all these are open intervals.
Okay.
Perfect. Yes.
Well, like in the interval negative 1 to 1, would you have to exclude the point at 0 because it's not increasing the entire time and there's a spot where it's not?
That is, you can write it as negative 1 to 0 union 0 to 1. You can, if you want.
I was just curious.
Because at any point in time it's not decreasing and not decreasing. Not increasing, not decreasing. I agree with that. However, the trend says between negative 1 and 1 is increasing. That's good too. Okay, before we continue with the second derivative, which we will look at in a minute, I would like to determine the x-intercepts. Obviously, this is the y-intercept. When x is 0, y is 0. I would like to find the x-intercepts of this function because if we graph it, we need those points. Always. So number 5, x-intercept. So I will copy the function here. So h of x was negative x cubed, 3x squared minus 5. How many solutions will we determine? What is the degree of this function? Degree is 5. Degree is 5, and we have to determine 5 solutions. Some of them may repeat. So when I solve the equation h of x equals 0, we have to find 5 solutions. Can anyone help? First 3 are x equals
0.
Perfect. Do you remember from pre-calculus what multiplicity 3 does? It's okay if you don't. This is multiplicity 3. In other words, the solution x equals 0 appears 3 times. Multiplicity 3. Do you remember what that does? It's okay. No problem. We're going to figure it out in a minute. And I will come back and write it here for you. Okay. Now when I solve 3x squared minus 5 equals 0, I get x squared equals 5/3, and I have to take the square root. So one solution is the square root of 5/3, and the other one is negative the square root of 5/3. I'm looking for my calculator so I can determine that. I put it in the table. So the square root of 5 divided by 3. I got 1.29. So approximately 1.29, approximately negative 1.29. So I go back to my table. I need those numbers in there. So 1.290, negative 1.290, and 0 is here. Okay, ready? We're going to look at the second derivative now, and we're going to talk about the second derivative test and also what the second derivative tells us or tells about the function. Ready? Okay, so the second derivative, I'm going to copy this and differentiate this. So 15x squared minus 15x to the 4th prime. So this is 30x minus 60x to the 3rd. We are going to solve the equation second derivative equals to 0. So negative 60x cubed plus 30x equals 0. I know you know that I'm going to divide both sides by negative 30 and get 2x cubed minus x equals 0. Pull out an x. 2x squared minus 1. As I said, there is no simple problem in this book. We will get three solutions. X equals 0. When we solve 2x squared minus 1 equals 0, we get x squared equals 1/2. We take the square root, and we get x equals the square root of 1/2, and x equals negative the square root of 1/2. This is approximately, my table is getting very crowded, the square root of 0.5, 0.71, negative 0.71. So we go back, 0.71, 0, 0, that's negative, and 0.71 and 0. Negative 0.71, 0, and 0.71, and I wrote the zeros correspondingly in the row for the second derivative. Okay. This is the second derivative. Now I have to study the sign of the second derivative. You can factor if that's easier. like negative 30x, and this is 2x squared minus 1. And now I'm going to plug in to the left of negative 0.7, I'm going to plug in negative 1. With negative 1, this is 2 minus 1, so it's positive. With negative 1, it's negative 1 times negative 30. This side is positive. Now this is going to be difficult because I have to plug in negative 0.5. With negative 0.5, this will be 1/4, right? Negative 0.5 is 1/2. 1/2 squared is 1/4. Times 2 is 1/2, so this will be negative. With negative 0.5, this will be negative, so I see 3 negatives. Now with 0.5, this will still be negative, but this will be positive, and this will be negative, so this is positive. Now I'm going to plug in 1, this is positive, and this is negative. Okay. When the second derivative is positive, the function we say holds water, opens upward. So that's the symbol I need. When the second derivative is negative, the function opens downward. And this is the symbol that represents that. And so on and so forth. Now I have 2 more x values in there, so I have to find these 2 y values. One for negative 0.71 and the other one for 0.71. How did I get 0.71? From the square root of 1/2. This is what I'm going to plug in, not the approximation, in this function. So in y equals, okay, so in y equals, I will plug in 5x to the third, 5x to the third, and then minus 3x to the fifth. And I'm going to plug in, oh, it changes, goes back to, I forget this, goes back to the default, no, okay. So I will plug in the square root of 0.5. So when we plug in the square root of 0.5, we get 1.24. How can I plot 0.24? Nobody knows. But because the function is odd, when I plug in negative the square root, I'm going to have to get the same thing, but negative. Okay? So, go back to the function, into the table, and we get negative 1.2, and positive 1.2, and negative 1.2. Okay. What does this point represent? Negative 0.71, comma 1.2. When the second derivative is 0 and it changes sign, this point will be called the point of inflection. Why? Because the function all of a sudden changes from opening upward to opening downward. This is not a max or min. The function does this. That point is called point of inflection. So negative 0.71, comma 1.2 is an inflection point. What can we say about 0, comma 0? The second derivative is 0 and it changes sign. What will 0, comma 0 be? Another inflection point. Finally, what is 0.71, comma negative 1.2 when the second derivative is 0 and it changes sign? Another inflection point. And now let's discuss the second derivative test. Here's what the second derivative test says. And you decide whether you like it, you use it. If not, I'm not going to force you to use either one. Don't erase anything. I just want to discuss this, and we will draw a conclusion together. The second derivative test says this. If the second derivative is positive, which means the function holds water, and somewhere in there, the first derivative is 0, -1 comma -2 must be what type of point? Right. If it's a minimum, what should be the sign of the first derivative before the minimum? Negative. And after the minimum? That's it. So that's what the second derivative test says. If the second derivative is positive and somewhere inside that interval, the first derivative is 0, then the sign of the first derivative must be negative and positive. So when is this used? When would I ever use it? When I don't want to, for whatever reason, I don't want to study the sign of the first derivative. How did we come up with that? So we looked at the first derivative, bless you, and we picked a number here, 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 and we determined the sign of the first derivative. So we put the signs in here. Let's say we don't want to do that, but then we have to wait till we find the second derivative, study the sign of the second derivative, and then automatically we will know the sign of the first derivative. So it's up to you. So now here, the second derivative is negative. The function opens downward. And somewhere in that interval, the first derivative is 0 at 1. What type of point will be 1 comma 2? Before that point, what will be the sign of the first derivative? And after that point?
Negative.
That's what the second derivative says. Second derivative test says. Now, I prefer to study the sign of the first derivative, but that's me. I will not force you to use either method. I prefer to study the sign of the first derivative because this is how I check my errors here. If this row works well with this, then I will figure out immediately. I don't want to wait till I determine the second derivative, study the sign of the second derivative, and then come back to find the sign of the first. The other reason why I don't like to wait till here, sometimes this will be difficult to determine. It could be a difficult function to work with. I may not even want to find the second derivative. That's one other reason why I put it in the third row. I may not even want to go that far. Maybe I have all the picture and I don't need anything else. So that's why that's my preference. Did you understand the difference between the first derivative test and the second derivative test? Should I repeat that? Okay. So now we are ready to graph. Of course, the only thing that does not fit in the chart is the symmetry. And if you remember, if we replace x by negative x, this will be the opposite of the function. So for now, let's just graph the function and so you understand how the chart or the table works. Okay. It's not an easy task to plot all those negative 1.29 and 0.71. We're going to do a very good job though. Okay, so I'm going to say this is 1, 2, 1, 2, and then 1, 2, 1, 2. Okay, I will plot the first point, which is negative 1.290. Okay, I'm going to say it's this, and then the other one on the other side, which is this. I'm going to plot negative 1, negative 2, which is right here, and 1 comma 2, which is right here. Then negative 0.71, 1.2. Negative 0.71, 1.2. And 0.71, negative 1.2. And of course, 0, 0. Ready? Okay, so let's see how this works. The function is coming from positive infinity, decreasing, opening upward towards negative 1.290. Decreasing, opening upward towards this point. Continues to, at this point, continues to decrease to negative 2 to this point, negative 1, negative 2, still opening upward. So now I'm going to erase that because I wanted it to look more natural. That was not the right direction. I didn't want to force anything. Good. So negative 1 comma negative 2, this is a local minimum. It continues to open up, but this time starts increasing till the first point of inflection. What did I do? Was this negative? Yes, sorry. It's right here. See how I catch my mistakes when it doesn't work? Doesn't make any sense. Okay. So it continues to open up, but now it's increasing to this point of negative. This is negative and this is positive. Okay, right here. Where it changes concavity because this is an inflection point. All of a sudden it starts opening downward, but it's increasing towards 0, 0. Where it has an inflection point. Now it changes concavity, increasing towards this point, opening upward. 0.71, 1.2. Continues to increase. This is an inflection point, but now it's opening downward to the maximum, local maximum. Then it crosses at 1 comma, at 1, where is my 1? Yes, this is my 1 comma 2. And then it decreases, opening downward, crossing at 1.290. We cannot find this much information about the function with the graphing calculator.